Everyone, let's talk about power flow in a parallel plate waveguide. Now remember, from electromagnetic field theory, we have this idea, a thing called a Poynting vector, which was defined as 1/2 times the real part, so R sub E, RE, of E cross H conjugate. You may or may not have learned this in some of your earlier classes, but this particular vector here represents the flow of power density. So it has units of watts per square meter. So the idea is you have, say, some electromagnetic wave and it's propagating through space. You have some kind of a square aperture here, okay, like so. Right, and some of those fields may strike this aperture and maybe propagate through it, right? So you imagine maybe it's a screen like so with a hole in it. Okay, and there's real energy in those electromagnetic fields. And you can capture that energy and do actual work with it. So the electric field itself doesn't actually carry energy. The magnetic field doesn't carry energy. But when the two are together, you get a wave that is propagating. And you represent it with this vector here, usually denoted with S. And it's called the Poynting's vector. So P-O-Y-N-T, Poynting's vector, or just the Poynting vector. Okay, so there is a derivation for this, which you might learn if you take an advanced EM class, but we're just going to kind of take it as a given. I believe Posar's textbook talks about this in the first chapter as well and gives a brief proof of it. So we're going to accept it without proof that this is a measure of the flow of actual power in an electromagnetic wave. And you notice it's a vector. That is, I can have this wave here, and it may have a direction associated with it at various points. And the way I would add it up into real power is you can imagine, say, if I have just some real power flowing here, I would capture it in this aperture. And so then the power would be my Poynting vector times the area here. Okay, and by area, you can imagine the length times width, and it'll have, say, a vector associated with it with its normal, right? So a wave going this way will capture less power than a wave kind of striking it directly. So you kind of have to think of it as this dot product here. And if I integrate this vector even over this particular area here, then I can even account for the fact that this is maybe not even a constant value across that little aperture, which is going to happen in a waveguide. So just keep in mind, this vector here represents the flow of real power, and it may even vary across space and time. So we remember my electric field was the following form. It was a summation A sub n sine of gamma sub n y times e to the minus j beta sub n z. That just went from 1 to infinity. And these propagation constants were obviously, we had gamma sub n was n pi over d. Then I had k was omega over c. And then I had this beta n over here, which was kind of the square root of that difference. So that little Pythagorean relationship here. We then found that the curl of E was proportional to j omega mu naught times this H field here, which meant I could solve for my H as simply saying -1 over j omega mu naught times the curl of E. And what that evaluated to was, you imagine there would be some, there's an x hat here on this direction here. There's a vector. So this had y and z components to it. So I could say hy y hat plus hz z hat. And we solved for those in another lecture here. So this parameter here, E cross H conjugate, so if I were to conjugate this, these would just have little conjugations on them. This cross product is going to be something like the following: x hat ex, I'm going to cross that with hy conjugate y hat plus hz conjugate z hat, like so. Now, consider a waveguide I don't really care if there's energy kind of bouncing up and down like so in my waveguide modes. What I care about is here's some little aperture in my waveguide, and I only care about the flow of power, the net flow in that direction. So what I only care about is the z component of my Poynting vector, right? Because if I have a tangential bit here, it's just going to sort of bounce up and down, but there's energy that's inevitably going to flow down this waveguide. You can also imagine that it really doesn't matter where I take this measurement. I could put it here at z equals 0, but I could move it over down a meter on the waveguide, and presumably real power will still just be conserved and flow down the waveguide, if it's lossless, right? Which we're kind of assuming in the ideal case. If it's lossy, of course, I would lose a little bit of energy as I move down, but if it's lossless, then energy has to be conserved as it propagates down this waveguide. So it won't really matter where I do this measurement. So for all practical purposes, we might as well just pick z equals 0 and just throw that particular little term away. So I only care about the z component of this vector here, and I only care about, say, at the z equals 0 point. So you notice I have x hat cross y hat will give me a z hat s sub z, and then the x hat cross z hat will be a y hat sy. But I don't care about that. So if I just dot this with my z, I will get only the z bit here. So I will not care about this little guy here. So in effect, what you'll get is the following: z hat ex hy conjugate, and then x cross z, if I can do that in my head, I believe will be negative y times hz conjugate. But we don't care about this little particular piece of it here. So this is the only bit of my Poynting vector that I care about at the end of the day. Now, remember, we did a calculation on hy, and what we got was hy as a function of y comma z gave me another summation from n equals 1 to infinity. So let me get my notes out here. Here we go. And we got the following. It was a sub n. There's going to be a beta sub n over omega mu naught sine of gamma sub n y. And we're going to pick 0 for z, so I'm not going to worry about the little beta bit. So you notice I still have this kind of Fourier series. It's just that the magnetic field, this particular component, has this little scale factor in here for each of these modes. So what I'm going to do is I want to calculate the linear power density going down my waveguide. So I'm going to denote this as a P prime to indicate that it's not watts per se, it's watts per meter, because this thing is infinite in extent along this direction. So if I want actual watts, I have to define some width here along my direction outside of the paper. But that's okay. So this will have units of watts per meter. And it's just going to be 1/2 times the real part. And we're going to do an integral from 0 to d of ex hy conjugate dy. So you notice I am just integrating that vector from 0 to d, right? So y equals 0 and y equals d. This is all I care about at the end of the day, which you can think of as being, the integral from 0 to d of my Poynting vector dotted with my z direction, integrating along y, like so. And of course, there's the 1/2 of the real stuff here we have to do at the end. So I'm going to kind of not worry about this just yet, because this integral is going to be the thing that's going to take up the most time. So what you're going to get, just 1/2 real, and this is just assumed here. So I guess we'll just kind of explicitly put it. So I'm going to get the integral from 0 to d. So I'm going to put in the Fourier series for my electric field, which is the summation from n equals 1 to infinity a sub n sine of gamma sub n y. So remember, that's my ex component here. And then my this is ex, so let's kind of label this real quick. So that's my ex. of y. So we set z equals 0, so that's okay. And then over here is going to be a summation. I'm going to say m equals 1, so not confuse it with the n's. And I'm going to get a sub n conjugate, because we're conjugating this little bit here. And there's going to be a beta sub m over omega mu naught times sine of gamma sub m y. Okay, and we're integrating across y. So this whole thing here is my h sub y conjugate for my Poynting powered vector here. And of course the units implied at the end of the day will be watts per meter. So that's where it's a linear power density. So this looks a lot worse than it really is. It kind of looks worse because I have a summation, all these terms, multiplied yet another infinite summation. So we're going to do a little quick piece of trickery. I'm just going to write this 1/2 real part. Oh, and of course, do that for the closed bracket on my real. I'm going to just flip-flop the integrals with the summations here. So I'm going to have a summation from n equals 1 to infinity. Just bear with me. M equals 1 to infinity, like so. These constants are going to come out. So an, am conjugate. The beta over omega mu naught will come out. And I'm going to have the integral from 0 to d sine of gamma sub n y sine of, sine, not sim, gamma sub m y dy. So this is the exact same expression. I just rearranged the order of things. Again, the integral is a linear operator, so I can move this stuff around, no problem. And then this is all enclosed in that little real thing. So remember, in the previous lecture, we actually calculated this. This little guy here, this whole big nasty integral. So remember, I'm doing this double summation here, but all of these terms evaluate to the following: delta nm, and there's going to be a d over 2 multiplier. Because remember, when we did orthogonality, I put a 2 over d to kind of normalize it. Otherwise, I'll get a d over 2 here. So what that means is all of these terms, all these cross terms go away, and the only thing where anything matters is when n is equal to m. So what we'll get is the following: 1/2, so real part, and I hope I don't bump into this, but I'm going to get the summation from n equals 1 to infinity, a sub n, magnitude squared, beta over omega mu naught times d over 2. Now notice everything here is real, and this is actually going to be a beta sub n. So I should have put a little sub n there as well, because we had it implied up here. So only n equals m matters, so this is what we get at the end of the day. So everything here is real valued, except maybe this particular constant here. So what we're going to get is, okay, I'll write this out again, a sub n squared, and I'm going to get times d over 4 omega mu naught, and there's going to be a summation from n equals 1 to infinity, or sorry, yeah, this summation should actually be out front, so I'm gonna move this over here. A sub n squared, that needs to be inside the summation, and then I'm going to get the real part of beta sub n, like that. So that is my equation at the end of the day. So you notice each one of these little terms basically represents the power flow in a particular mode. And if I have a bunch of modes, I'm just adding up the powers kind of in each individual mode until something special happens. Remember, beta n is equal to the square root of k squared minus gamma sub n squared. So as long as k squared is bigger than gamma, this will be purely real valued, and nothing special is going to go on here. And that real parameter becomes kind of redundant. But eventually this gamma gets really, really high for the high order modes, and this whole expression suddenly becomes imaginary, and you get something like j alpha sub n. So these are the cutoff modes, right? And in that situation, this real of beta suddenly becomes 0. So you can think of this as sum over all propagating modes. And then all the cutoff modes contain no actual net flow of power. Right? So that is how you calculate the flow of energy down a waveguide that is excited by multiple modes. Only the propagating modes, that's in contrast with the cutoff or the evanescent modes, will have power. And then when it's evanescent, this real term suddenly goes to 0 and all those further terms vanish. Okay, so this is why we say that a cutoff mode or an evanescent wave carries no actual power. It has electric fields, it has magnetic fields, but this little real term suddenly means no real power is going to propagate. There is still energy in it, but it's a lot like the energy in a capacitor per se. It's stored energy, but it's not really flowing energy in the sense of an electromagnetic wave. So if I have a wave like this and it's propagating along, it will carry real power with it. But if I have, say, how did we draw that? So you could say, here's my sort of evanescent decay modes, if you remember those pictures. you had the mode profile here and they exponentially sort of decayed. There's energy in those fields, but there is no actual power flowing down in them. So again, you would say it's reactive power. So there's actual energy in the field, but it doesn't carry energy anywhere. It's more storage. Okay, so that is the idea of power or energy propagation in a waveguide.